I would like to invite Professor Silva. Welcome.
Welcome. So thank you for the opportunity to present in this webinar. My work is about fractional boundary value problem, a particular class of fractional boundary value problem. And this is a joint work with Professor Luís Castro, also from Portugal. Our motivation is on fractional calculus and Ulam-Hyers-Rassias stability. So we studied stability, in particular Ulam-Hyers and Ulam-Hyers-Rassias. We know that the fractional calculus was used in many areas of science and engineering, since many systems can be describing by using fractional differential equations, and in particular with boundary conditions. And on the other side, these problems have a particular problem, which is find the Z solution. And because of that, the Ulam-Hyers and Ulam-Hyers-Rassias are so important. This stability permits us to obtain a very close solution, a very close approximation to the solution. And it is important because the Z solution in most of the times are difficult to reach. So I will present some basic definitions to this work. I will present the fractional boundary value problem that we studied. I will present the solution, the existence of the solution. The principal technique that we use in this work is the Banach contraction principle, which is used in operator theory, very used in operator theory. And I will finish with the study of the uniqueness and Ulam-Hyers and Ulam-Hyers-Rassias stability. So the operators that we are using are the Riemann-Liouville fractional integral operator, which is defined by this way. Here we have the gamma function. The interval is defined between 0 and infinity. Alpha is the order of the integration. And we use the Caputo fractional derivative of order alpha greater than 0, which is defined by this integral. Gamma is again the gamma function. N is the integer immediately greater than alpha. So alpha is between n-1 and n. And here we have the derivative, the usual derivative of n over t minus s elevated to alpha minus n plus 1. With these derivatives, of course, this derivative, when n is equal to alpha, we have the usual derivative. So the problem that we study is a problem that we can find in this paper of 2011 of Zhao, Shai, and G, where they studied a problem like that. Here we have the Caputo derivative of order alpha. In particular, the alpha that we consider in this work is between 1 and 2. Lambda is a positive parameter. Xi and eta that appears in there are constants between 0 and 1. Beta that appears here and gamma that appears in here are constants between also 0 and 1. We have this particular thing that is the Xi is less or equal than eta. The function f is a continuous and non-decreasing function for each t between 0 and 1. T is between 0 and 1 is the interval that we consider. X that appears in here is a positive function. Moreover, to obtain the solution, the authors the authors Zhao, Shai, and G consider this particular condition, which is important along all the work, which is the relation between these constants beta, gamma, and eta and Xi, which should be less than alpha minus 1, which is the order of the integration, times 1 minus beta Xi. This in particular, it appears when we are obtaining the solution. So in the rest of the work, we will consider always this condition. Zhao et al. Proved in 2011 that the solution of this problem in here don't have the lambda that we use in our work. They proved that for that problem without that lambda, the solution is given by that expression where we have the Riemann-Liouville integral in here of this function f in t, c1 and eta, and we have this constant delta, and of course this is not a constant, there is a t in these expressions. We usually, in the fractional boundary value problems, we rewrite the solution in terms of the green function. So we can rewrite the solution in terms of the green function, which is a function like that. Of course, we will not explore that because it is too big to explore in here. So the integral between 0 and 1 of the green function here defined times the function f, this continuous and non-decreasing function. When we consider the problem with that lambda, the solution will be given by that expression where the green function is given as in the previous lemma. The authors Zhao et al. also studied that the green function satisfies some properties. So we consider again this property, this condition along all the work. The green function satisfies in particular this first one property, which is the most important for our work. The green function is positive and less or equal than a constant m, and m defined like as this expression in here, times 1 minus s elevated to alpha minus 2, when t and s belongs to 0, 1. So in what follows, we will use this condition 1, not the second one. As about the Banach contraction principle, the Banach contraction principle said that if we have a generalized complete metric space, if we consider a mapping that is strictly contractive, this means that when we compute the metric, I will call that the distance, but this is a metric. So when we compute the distance between tx and ty, this is less or equal than a constant, which is a constant between 0 and 1, less than 1, not equal than 1, times the distance between x and y. When this happens, we say that the operator t is strictly contractive. And if the operator is strictly contractive, we have these properties, the mapping T as a unique fixed point, and we have the following inequalities. In particular, since we are dealing with continuous functions, we will not use the derivatives, we will use the last one property in a theorem that we proved. We use the Banach space of continuous functions from I in our case is 0, 1, with finite norm defined by the supremum of the absolute value of x. So this is a Banach metric space, and we will use the usual metric in Banach metric space. When you talk about Ulam-Myers stability, we talk about the following definition. The problem that we are studying is Ulam-Myers stable if there exists a constant k greater than 0, such that for each epsilon and for each solution, each solution epsilon that satisfies this inequality. I remember that the problem said is very similar than that, but we have in here equal, not the absolute value, and have in here equal to 0. So when we are talking about Ulam-Myers stability, we consider a solution of the inequality, not equality. In here we have the inequality and absolute values. So if this epsilon satisfies this inequality with the initial conditions, there exists a solution, an exact solution of the problem, such that the distance between x and y is less or equal than k epsilon. So if we are considering a solution epsilon satisfying that, we can say that there exists a function g in this space, which depends on epsilon, such that the modulus of this g is less or equal than epsilon, and g is defined precisely by this way. So g is the expression that appears in the modulus. The initial conditions are again satisfied. And we use this in particular to study the stability. So this is the problem that we are studying. This is the M that we have defined before. We will suppose always this condition, as I said, and we obtain this theorem. F is a continuous and non-decreasing function such that F satisfies the Lipschitz condition, where this L is greater than 0, and this function F as a supremum that we call N. This is a finite supremum. Then the fractional boundary value problem is Ulam-Hyers stable if we assume that the L that appears in here is less than alpha minus 1 over lambda M, the M defined in this way, and lambda that appears in the problem. To prove that, so we consider the solution that I show you at the beginning of this presentation. This is the solution of the problem, the general formula of the solution of the problem. And we consider an operator T defined as a continuous operator from 0, 1 to R plus, and define it by this way. And we transform our problem into a fixed problem, into a fixed point problem. So the eventual fixed points of this operator T will be the solutions of the problem. And if we prove that the fixed point is unique, then we have a unique solution. It's because of that we applied Banach contraction principle. With this Banach contraction principle, we will show that T as a unique fixed point. This is the idea of the proof. To do that, we first prove that T maps C01 R plus into itself. To prove this, we consider this supremum of the function f. We choose an R which is greater than that. Since alpha is not equal to 1, this is defined. And we consider the balls such that the norm of x is less or equal than at R. And now we compute the modulus of this Tx. We use the measuration that the measuration that we know for the function, for the green function. We use that in here. We use the fact that f has a supremum n, and we obtain that this is less or equal than R. So we prove that TBR is contained in BRs, since we have the continuity of function f and green function, we also have that Tx is continuous. On the other hand, we have to prove that T is strictly contractive. To prove that, we compute the distance between Ty and Tx, and we obtain, and we can compute that. We use again these inequalities, and now we use the maximum of this green function that we know it is in here, and we use the Lipschitz condition to the function f that is in here. We know conditions. We are imposing a condition to this L, and imposing this condition, we obtain that the constant in here is less than 1. If it is less than 1, T is a contraction. And so we conclude that the T as a unique fixed point, which is the unique solution of the problem. Now we have a unique solution, and we will prove the stability. To prove the stability, we consider the function g as I defined it before, which comes from this inequality. This function g is the modulus of this function g is less than epsilon. We compute. So epsilon can be written in this way. If we assume this g, we can obtain this solution. And now computing the distance between x and y, we obtain these inequalities. We will use again the supremum of the green function, and also we use the Lipschitz condition on f, which appears in here. When we obtain this expression, we have in here the modulus of x minus y, and we have again the modulus of x minus y in the integral. So to go over this problem, we use a technique, a known technique, which is the Grunwald's lemma. The Grunwald's lemma says precisely that we have epsilon less or equal than a k, the integral of h times epsilon, where epsilon and h are non-negative functions, then we can measure this epsilon by this way using this exponential. So we use the same technique, and we prove that x minus y is less or equal than this exponential, and we have precisely epsilon times another constant. So we conclude that the fractional boundary value problem is Ulam-Hyers stable. We also proved Ulam-Hyers-Rassias stability. Ulam-Hyers-Rassias stability is very similar, but in here we use a function from 0, 1 to r plus. We use another constant k, and the difference in here, the difference between Ulam-Hyers-Rassias and Ulam-Hyers stability is that this expression in here is less or equal than epsilon times this function f, this positive function. And also, assuming that those conditions, we obtain at the end that the distance between y and x is less or equal than a constant times epsilon times the function. So the proof is a little different, because when we consider the function in here, we have some other difficulties. We consider again the same as in the previous one. We consider again a new function h, a continuous function, which modulus is less or equal than epsilon phi, since h is defined precisely by the expression that are in years inside the modulus. The initial conditions are again the same. For this case, we obtain that assuming that initial condition, considering the function f, which should have a finite supremum, we assume again the Lipschitz condition, and the fractional boundary value problem will be Ulam-Hyers-Rassias stable with respect to this function phi. So to prove that, we consider again the operator t as a unique fixed point. The formula to prove that is similar, is equal to the last one, so I will not show it again. And now we consider an epsilon, which be the solution of this inequality. We consider again this expression, we consider this h, where this h is less or equal than epsilon phi t. It means that we can rewrite epsilon in this way. We fix the notation M1 and M2, M3, which is the constant that appears in the solution when we write the solution in terms of the Riemann-Liouville integral. And we calculate the distance between y and ty. We obtain that expression using, we impose the conditions that M1, M2, and M3 are positive. Of course, they are positive. The K1, K2, and K3 are positive, and we impose that these M1, M2, and 3 have a finite modulus. And in this case, calculating this y and t minus y, we obtain precisely this inequality, and thus we obtain that y minus ty is less or equal than k epsilon phi. We use the Banach contraction principle, which says that the distance between y and x, y and the exact solution, is less or equal than 1 over 1 minus L. L is Lipschitz condition, times k times epsilon times phi. And so we obtain, since this L is defined using the L that we have obtained before, we obtain that this is less than this this and we conclude that the fractional boundary value problem is Ulam-Hyers-Rassias stable. So this is four of the references that we used. In particular, the papers where the paper and where the problem is presented. And some of the recent proofs in the uniqueness of fractional boundary value problems. So this is all. Thank you very much for your attention.
Thank you, Professor Silva. Is there any question or comments, dear attendees?